We are going to move, I think, to our third speaker. His name is Alejo Sanchez, and he's in the UK right now, but I actually had the luck of growing up with him in Buenos Aires, and he's going to delight us with an explanation of data indexing. So I think we can just jump into it.
All right. Well, hello, everyone. And thank you, Fede, Brujo, the rest of the guys, the rest of the presenters, for giving me this opportunity to present this interesting topic. It sounds a bit harsh, but it's something that there's a good opportunity to explain it in an interesting way, let's say. Let's jump into it. Usually in people studying computer programming or computer science and similar careers, this is one of the topics that is extremely important, but it's sort of glanced over. Or, oh yeah, you use an indexer, yeah, but it's not thought through. And then when you face things in real life, you might not be making the best out of them. And so with this, I'll start sort of from small to more advanced stuff. But let's say, okay, like why is this important? Why I'm an index, like data index researcher? Like why is this? Why does it matter? Well, if you can be a bit cheeky about it, like you have the largest company in the world, Alphabet, their main company is Google, and they are basically a search company. They search things in the web for us, and I don't have to tell you how valuable that is for humanity. Not just because it's Google, but it could be any other company that's doing that service. At the moment, it seems to be Google. What's it like? Where's this coming from? Why now, in end of 20th and 21st century, this matters more? We are starting to manage our lives and things that humanity makes more online, and that means we're cataloging information about the real world in the virtual world, be it the computer or the internet. And the way these computers work is very particular. It's not the same way as we do. Like we, as a human, when we have this system in our brains that when you see a face in a fraction of a second, it identifies the person, give you context. It could be, I don't know, say your relative or something, and in no time you go like click and you're there. You're in context for the person you're going to talk to, be it your boss or anyone. Computers don't work exactly that way, and also the human brain is very specialized for certain things. It does very well, like recognizing faces. But managing these large amounts of data is something that we cannot do well. And these computers, which in a way they're like a sort of dumb, very simple, dumb brains, but are really fast. Within very strict constraint, they can do a lot of things. So, well, as you see this presentation, I didn't make slides. I often use slides, but I think the topic is kind of hard, so I'd rather make it more fluid, so we can play with it a bit more. So let's dive into it. Like, let's say we have some numbers. I don't know. Let's say 14, 2, 22, 23, 7, 19, 5, 9, and many more. And let's say, and a number is sort of this one of the simplest forms of data. The simplest would be a bit, but to make things a bit more useful, we will start with a bit higher level with a number. But this applies to many other things like strings and other types of data which belong to some properties we'll see later. So let's say we have these numbers, and let's say they belong to a set, and you can see the set as like a bag. Let's say like a bag that is opaque. Like we know, like seeing this, we know this. But if there's here, say, a computer, it can only see from like either a tiny hole, or it can only pick one thing at a time. Yeah, it can do it really, really fast. It can look for billions of them in a second. Like we cannot do that. We can't see billions of numbers a second, but it can only do it one at a time. So what happens if we if we want to see if in that bag there's a number, I don't know, 55? Let's say let's fit now here. Like let's find this. The way a computer would, without any optimization, with nothing, if you just have a bunch of them, like we probably store some memory, something that will be our bag. It will be like, okay, pick one, see if like pick one, say this one. Is it this the one? No. Well, okay. Let's say let's put in this other bag, that one, and we keep picking numbers from our set. So it would be like 1, 2, 3, and going around until it finds the one that it wants. And so that's kind of a tedious process. And also every time that if you want to find multiple numbers, let's say you want 55, you want 2, you want 27, you want 15, this would be, of course, too obviously wasteful. So like let's think about, like, let's just slow down a bit. Actually, the way usually this is sort of glance over, but this is very important in the meaning of it. Like, what are we doing here? We're doing a comparison, and this comparison, what is it telling us? It's sort of yes or no. Is it the number we're looking for? Yes or no? We can see this information in this comparison, which is a comparison of equality. Let's say 19 is 19 equals 55. Well, for programmers, usually when we mean comparative, we use 2 equals. And this will give you this one bit of information, basically, because it's only 2 positions, like yes or no, true or false. And we do something about it. So what can we do about this? Like, there's something like, of course, you're probably already thinking, okay, oh yeah, those numbers are a mess. They are all around. Like if you see a hoarder's house, you want to find, you know, your slippers, and it's somewhere in some box, and they have all these piles of things in their house. It's a mess. So what do? You start giving some order in your house. So you say, okay, the top drawer is for socks. The second one is for underpants. So bringing order helps you in finding things within a large group of things, finding particular things in a large group of things. In the case of numbers, we can just we can order them, and there's something interesting now, because let's say we had from this, it will be like 2, 5. I'm ordering, as I say, 2, 5, 9, 14, 19, 22, 23, 27. What we gain here is like, if we do the same way, if you just compare one at a time, and if we go from left to right, you can say, okay, is this 55? No. Is 5? No. Move to the next. Is it 55? And if it's not present, we'll have to see the whole thing to say, when we finish here, say, oh no, I compared with everyone, and there's no 55 there. And if we're looking for something that exists here, the average time that we'll have to walk to get to the one that we are looking for, it will be half. Like if it's a random one in here, if we look for all of them, each one is going to take their position, and will be their position divided by 2, divided by the amount of numbers you have. So, and that will give you half. So there's something else that we can do here. Like, as I was saying before, like, computers are very particular. They cannot see, as we say, a whole face and context, okay, where you are, and do process with many things together, like, at least not in a normal way of working. So one of the things we can do here is like, okay, this comparison can do something more for us. In this case, that we have order. What if we can have greater than comparison? And with this, we can move, like if we can compare in any place in here, remember the computer can only see one at a time, but the properties, it can see any of this. It can move around, go from any position. If it can do that, the advantage is that even though the result of the comparison is still going to be is 55 greater than, say, 14, it's still true false. But at this time, you can discard half of the numbers. You're basically comparing that one, like, and all the ones on one side and all the ones on the other side. You're just comparing these two halves. And with this, we can go to the next step with this. Okay, how do I maximize this? Because if you compare halves, it doesn't make sense to start with the first one, second one, because if you can discard half, but half of the number is only one, you're in the same situation as if you are doing one at a time. As you probably, as intuitive, you see, if we start right in the middle, we can discard a lot in each comparison. So we can do that repeatedly, one after another. Let me switch to screen share. So screen share. So as you can see here, the way that this is going is that you get discarding, and you end up with a smaller and smaller range that is remaining to see if what you're looking for is present. I don't know if you guys can see my my mouse pointer.
Yep.
Oh, perfect. So basically, what you need to keep track of is what is remaining of your range that is moving around. I'm not going to go into details on how to implement this because it can be a bit tedious. But the big thing here is this. Okay, this is called binary search, and it's binary because in each step of the operation of the algorithm, you get only one binary value as a result. But it's not binary that goes only you advance one bit of the actual set of data. You get information about whole chunks of it, and it's very efficient because you can prove this, that since the range gets smaller and smaller very quickly. You're going by half and half and half and half and half. This is the amount of comparisons that you need to do is the logarithm base 2 of the total numbers that you have in the set. So this for very small ranges that you don't see much, but when you have I don't know, a few billions, you can, with only 32 comparisons, you can find a number instead of 4 billion. So the difference is extreme. So, but let's move to next. So this is kind of a simplistic example so far. Let me stop sharing. So, so what, like, it's not common that you have just numbers and see if there's a number inside of a set. Usually you have something like, let's say, an inventory table. You're a store like Amazon store, and you have the item ID, say, I don't know, a pen drive. It's a pen drive and you have the brand, and you have how many you have in stock, and you have what's the price, and the description text, and a bunch of other things. Maybe when is when it expires, if it has expiration date, and all that, or on what storage facility you have it to deliver it. So this is something that happens and complicates things a bit. Like you could have this table of items, and let's imagine there's a lot of them. And to do the binary search, you have two problems here. First, you can only order by one thing at a time. Like you cannot order by say the item ID and then for something else. You can do one and the other sort of cluster. So you say for the first value of the item ID of the you can order by then the second, but it doesn't make much sense in the case of say item IDs because each one will be unique. So you cannot order by how many you have in quantity for each. You can use the same order in two things. So that's one problem. And the other problem you have is what if you want to insert into that table of items something that goes kind of like in the middle. Like you have this list of items, and you have a new one. Let's a new item coming. Let's say a bigger one. You have here the pen drive, the 32 gigabytes, and here is coming a pen drive of 64 gigabytes of the same brand. If you have it all together, like flat out as it is, you have the problem that you cannot put in the middle. You have to move all the others down to do that. And if you have billions of things or a large quantity, that's extremely impractical because all your inserts become extremely expensive. So, and also, yeah, and you have that, like you have the, say, the item ID, you have the quantity, and other things. Sometimes you want to look for, okay, which products have the most quantity or which products are in zero because they only need to order for new ones. So for that, the way to do it is you have an auxiliary table, like it's like an index you have in your book. You put an auxiliary table, and that one can have or more. One auxiliary table could be by quantity, let's say. So be the index. And in here, we can have this table ordered by the quantity column, but it wouldn't make sense to repeat the whole thing because this table could be very big. As I was saying, we have like the text description, what storage facility is it present, or any other text related stuff. Well, there could be a lot of columns in there. So what you have here is just the quantity value that you're looking for and the position in the original place. Let's say it's here, and this one was here, this one was here, and they're like that. So in here, in the quantity index, you can do the binary search again if you look by quantity, because this is ordered by quantity. But again, you have the problem of what if you want to insert something, because now, yeah, you can put in the end, like at the end of the table, and then have this pointing there. But then you move just the problem here. Like, how do you insert new entries in the index? So for that, what you need is a data structure that is not fixed. It can be an array. If it can be modified, like it can be extended in the middle. And the most common one to use for this are trees. Like this, the tree data structures are represented in memory or disk in a particular way, but the way they usually happens is like this. Like you have one value or more. This goes to, let's say, binary tree. Let's go for a binary. Let's say this one has 2. We can go on like this. And in here, we can do the same trick of the binary search. That could be, because it's a binary tree, like each one, like let's say this one has also 2. So this is a parent or root. These are the sort of the root's children. And these 2 and these, let's say 2 more here, are the grandchildren of root. We can do the same thing for applying the same principles of the binary search with a tree in this case. In this case, we have a reference, like a position in the memory, not a position in the table, of where are the children. So we can do a comparison with, say, the root. And when you have the comparison of the root, we can have half. This, if we display this logic, it will be this root.
Sorry to interrupt. Could you move the camera or the sheet a bit lower?
Oh, yeah. Sorry.
Brilliant. That's perfect.
Sorry about that. So, so yeah, logically, like you see, every time you do a comparison, you split in half. If you compare it with the root, you only have remaining half of the tree. If you compare it with this, you only have this or this. So we're still doing a sort of binary search. And in this case, it's called binary search tree, or BST. And binary search trees have a lot of interesting properties, and a good thing is that here you can move things around because they are not together. These are references, like that's why I put them separately and then put in like in a table. Like you can, let's say the new child of root is this other thing now. It's not for some reason it was an insert, and let's say this one is to this, and sets other things in here. With this, we gain the property of inserting things somewhere and keeping the property of looking things in with the logarithmic amount of comparisons, and not a full scan of the table. Full scan is called when you go sort of sequentially, like one from the start to the end. So, so with these trees are nice and interesting. But they are not very efficient, because here one of the problems that you have with this is that, as I was saying, these nodes within this tree will have references. The way we represent this, this will be like a node for root. We have root's value, the pointer to the left child will be this thing, and the pointer to the right child. And since we're talking about large amount of data, like usually in modern computers that are 64-bit, the pointers end up being 8 bytes. 64 bits divided by 8, which is a byte, gives you 8 bytes. And this can grow quite much. And let's say if the quantity of that we were comparing, our indexing, this was a number that is, say, typically 32-bit. And you have 64-bit, you have 64-bit. We have a problem that, well, here, yeah, the size doesn't represent at scale. But the problem we have here is that we are wasting 4 times the original size of the value in just the pointers. You see, and that this brings a problem that indexing in general has. Like, what's the overhead of the index in size compared to the values that it's indexing? Because you see here, just one little value here, but if you have a table with many columns, and we have these binary search trees for each one of, or many of those, the size of the indexes that are referencing this table could be, it's much bigger than the column. Like here, you have the size of the column would be included in this, but this would be 4 times bigger. So in this case, it's 5 times bigger than this of the column if it's indexing. So and also there's a problem that the way you advance and you move in the tree, like these jumps, like with these pointers, give you really nice freedom, and you can insert things very quickly. But you have the problem that each memory access, if going to all the way to a memory, is not completely cheap. There's actually something you probably heard, like the cache of the CPU, and that is separate from memory. You have the way that CPU accesses it. It goes first to see in this sort of goodie bag of things that recently been kept. Okay, is it here? It could be like your purse, something like that. Are things in there, like say your keys? Okay, look in there if they're not there, or your phone. Okay, oh, I have to look into the whole house where I left my phones or my keys, and it's much longer time to do it. And if we have to do that for a lot of these nodes, even though we reduce from say billions to 32 comparisons, we still might take a long time to walk the tree to get what we wanted. So there are some optimizations for that, and also there's some optimization for this that make that the binary search trees haven't been used much in the last couple of decades. This kind of data structure that was invented in the early 70s, I think. But the way they did it was that instead of having a whole tree thing, like a single node, they make a tree of groups of nodes. So they have this chunk here. And let's call this is the root node, but this is the root node of the tree. But this one has many elements inside. And this node goes to many other nodes. It's called a B tree. The idea here is to first to shrink the amount of pointers that you need internally to go around, like we had in the example before in the binary search tree. We had each one has 2 pointers, and so there was quite a wild west of pointers in there. And in this one, the idea is that, say, the first key compares for the second and the first and second, let's say. So this one technically goes to this one go to this one, and so on. And now, if you see the root node, you need pointers here to those arrows that I'm making. But here, for each element, which is for each one, you have only one pointer, and that pointer points to a child chunk here, the child block. So even though for the first one you have you don't have 2 anymore. You have per element you have only 1, so you just have the amount. So before we were saying that there was a 32-bit node with which is 4 bytes with the 8 bytes and 8 bytes. Oops, let's move it. Go here. 8 and 8. Now we move to 4 and 8 for each of these values. It's quite a shrinker, but still kind of big though. But yeah, another advantage that we get here is like accessing memory. Since these are all together, it's practically free. The way the caching system works, when you pick a chunk of memory that is all contiguous, all together, it's practically the same cost to access 1, 2, or 20. So each time you walk, and let's say this is again with billions of elements, each time you walk in here, like this is only a single access, and we can compare with many more elements. In this case, we have 7, but it could be 30, it could be 100. And the CPU can save in the amount of accesses to memory it has to do. And also, this tree has some other particularities. This looks okay, very simple, but there's a problem of maintaining, like these ones have to maintain order. So to do that, you need some sort of bookkeeping rules on how to keep this balance. The B is for balance in this case, not for binary. The usual algorithm, it kind of keeps things like if it's getting to 3/4 full, you split the node and make another one to the side, and so it will be like before we did in the binary tree, that we were adding some nodes, and by changing the pointer of the root and to creating the node, the new ones somewhere else, and change the pointers. In here, we would need to do the change of pointers in the parent, and then making more child nodes of the parent to to make room for new stuff. And also then there's the opposite. What if you add stuff but then you remove stuff? Okay, it also has some rules that, okay, if the node is less than half full, then, and the sibling is also less than half full, then you can fuse them together into a single node. And there are a bunch of other rules, but I don't want to get too too much into the details of the algorithm. So, okay, this B3 is interesting, but that's a further problem. What if there's a problem of, okay, how big is the tree for the internal node? Because usually you have, again, let's know that since our blocks like this. There's many more. The size of this tree, and say we have billions of elements, this will be with several layers. The size of the trees would be quite big. So if we try, the idea is to maximize how much we do in the walking of the tree, because this way, whatever we fetch from memory is more useful. Like, we don't fetch other information that is not immediately useful for us. So one of the things they do is, instead of just having the whole nodes of the original, of whatever original we're looking for, there will be because so far I was simplifying, we just say it's thinking the quantity, but actually it's a quantity and a position. So it's actually, I've been lying to you. So let's have it. Okay, so the node truly, because remember there was, where are we? Here. Remember that you had the original table and you have an index. Okay, let's put it here. So the index to this table that we're processing for a particular column. But here we were, I was forgetting about this one, which is a pointer or a position of the source table that we are indexing here. So it's actually the quantity, the position in the table, and then the pointers, say in this case to one down, and in the case of binary trees, we'll have another pointer with a left pointer and a right pointer. So keeping this information, if we do it this way, this pointer to a table is very wasteful to being, for every time, for every one of this, we'll have this other pointer. And again, if we're having billions, this will be also 8 bytes. And it's kind of wasteful. So the way this is dealt with is, this is called a binary plus tree, B plus tree. So, and what they do is that this in the internal, any internal node doesn't have anything but the key. So that in this case we're indexing quantity. The key is the quantity, the value that we're comparing. Remember, we're doing comparisons, but not keep the data, which would be the position in the original table, in any internal node. So the internal nodes are different. And let's say there's many layers, and this is the last one. These are nodes of the B plus tree, which have many elements inside. So let's say this one is internal, and since it's internal, it has the key value, it was a quantity, and nothing else, and a pointer to a relevant other block in the next level, and that's it. So now it's 4 and 8. Well, and what is called the leaf node, which are the last ones when they get to the actual elements. These ones are now, yes, you need the key would be, this is the key. We were sorting by quantity, and then yes, the position, which is, and this would be 4, 8. And the good thing is like now this internal pointer goes away because there's no other next level that we need to reference. So now we compacted all the internal stuff in just 12, while before with B trees, not B plus, would be quantity, pointer, position, and pointer. And this would be 4, 8, 8. So it's quite different. It's 12 and 20. Yeah. So what most of the most databases that you probably are using or you've seen around, the most common data structure to do this stuff is the B+3. And not just databases. This is used for file systems, which in a way, the file system is kind of a database of files. So the B3 is a very useful thing, and it's very good for permanent storage. Like for memory, it's not the best at the moment, but it does very well still for anything that you have to store on your disk or in network, for example, something that it's very costly to do the operation to walk it. So okay, we've been through quite a lot of ground, and I hope I haven't been going too fast. So now we are jumping into the things that happened in the last, say, 15 years or less than 15 years. For a good while, since B+3 were very efficient, very good one for the back, conservative in memory, there was not much interest in improving that. But now, since there was this boom of information growing with the internet and everything becoming online, there's now a refreshed interest in having these things perform even better than this, because we're still having with that, if you were saying, like each node in the B+3 will be 12 for internal and 20 for the end of actual value nodes. It's much bigger than the actual table, and also it's sort of spread around. Like the internal nodes of the B+3s or B3s are a bit hard to manage and a bit unpredictable too. They are very easy to when you add something, but then it's not that good to do things after. And there's another thing, like this now it's very common, what is called you've heard probably big data or data science and all that. And for us, people in the data and database areas, we call that sort of data science, and in particular, this for analytics, because you are doing analysis over data. And usually when people talk analytics or online analytics platform, I think it is the OLAP is the acronym. The particularity of that is that just with a lot of data that is processed, let's say for a massive online store, this all their sales data of the day or something like that, or I don't know, Google with all the new pages of the day or the new YouTube videos, I need to classify them or something. These things run in large amount of data that don't change. So these features that you have with the B+3s and B3s are not that interesting, because you're not adding stuff. You make them kind of once, you make the table, then you want to index it, and then you want to find a lot of things in there, process a lot of data. It might take an hour to process. And again, those features is just, and it consumes a lot of memory that you want to keep things in memory, not run it on the disk. Like the memory, to give an idea, is in performance-wise, for the unit of processing for a CPU in time, which is at the moment is a hertz, so, and a computer can run a gigahertz, so it's a billion units per second. The memory is about 2 orders of magnitude slower, so it's like 150 to 200 times slower than how the CPU can move things around. And the disk is, we're talking now with the SSD, like the fastest, and it's not a disk anymore. So we call them disk, but they're not disk. They're kind of persistent memory. They're like 1 million times slower or more, maybe 10 million times slower. So So it's the huge opportunity to improve things there. And some of this research that happened in last, this was 2007, I think it was, or 2008 or 9. There was a group at Intel and combined with Oracle and some and I think it's the University of California, Berkeley. They made this a new tree that is all for this kind of workloads. So it's this kind of processes that doing huge analytics on how to improve the memory access and how to make this super compact. So to get to this, let's start first with something that is quite interesting, like a way that we can express the binary trees. Some people call it binary heap, but you can do kind of like this. You have the problem of having the pointers to the children in the binary tree. If you go back to the original ones. So the cost that we were having here is that these things are whole pointers and they're very expensive because they take 8 bytes each. So what if we can get rid of them altogether? Wouldn't that be nice? So what if we put the nodes ordered in a particular way, one after another? Again, we have the root node here. And we can take, we can define the position of the children. Again, this is binary search tree, so it is each node has 2 children. And let's say root has which is in position 0, as the left child is says A, B, D. Has A and B. So A is this would be equivalent of having root A, B, C, D. So here we can do this. Okay, root goes to A and B. This is implicit. And then A has children C and D. And V can have children E and F. But the root is trivial. Okay, the children are the next 2. But as you see, you're sort of intercalating. Now we have the cis children, these children, E's children, F children. So there are blocks of 2 that are being added to the right. We can calculate this position from where we are standing with a very interesting formula. So let's see where. Okay. So the left one is in position 2n plus 1, and the right one is 2n plus 2. So in the case of 0, is 2n is when you're from root. So root is 0. So 2 times 0 plus 1 is the left one, which is A. 2 times 0 plus 2 is B. This is 0, 1, 2, 3, 4, 5. Navigational position, we save ourselves from storing pointers for the index. So this shrinks the index. Imagine if you originally with the binary search tree we have and the 4 bytes of the actual key value and the 8 of position plus the 2 pointers, the left pointer and 2 of everything off. So okay, so it's the right child. Let's move it here. We shrunk and we completely eliminated this, and it's even smaller than the B3 and B+3 is because those still has the internal nodes have pointers, and and we only save in the last one. They only have these two, but all the internals they have. Well, in here, every node has something that we can finish. Like we can find something in, say, maybe we were finding for D, and we need to go further. And we have this extremely useful navigational position. There are problems here, and again, the problems we had before. What happened with insertion? Okay, this order of things, it doesn't help. It's terrible for insertion. Every time you need to put something that is not at the very end of this tree, you need to basically reveal the tree or reveal a big part of the tree. It becomes useless. But for online analytics and many other cases, this is not the case. We just build it, sort of take the data of the day. So this is called usually a cut. So we cut the day and index it and make the tables that we want, an index of table with many of these indexes. And we just build them once, and we use them many, many times with a lot of queries and processing at night. Usually, yeah, I'm assuming at night, but it's the most common case. There's also another thing that this form of navigation is very useful for the current architectures, because the way the CPU uses these caches is, let's say, we have here the CPU. And let's say I put this bigger and different, so understand this is huge. Like this, the size of this is gigabytes, and this to typical computer, I don't know, 32 gigabytes. Let's say this is for service kind of small, and the cache is 8 megabytes. So it's so this would be 0.008 gigabytes of size. So it's much smaller. The way that the computer does this, that okay, it sort of keep this sort of pores of recently used objects to find them quickly in a much smaller place. The way this is done is with something called the associative n-way associative. So if you have, if say this is empty and the CPU wants to find this one, get this one, it brings a whole chunk. It actually doesn't read, like when you read, say, an integer from memory, the cache can't read an integer. It has to read a cache line. So it will read, and imagine we wanted just this one. So it will read the whole cache line, it will bring it here somewhere. But to make this, again, quickly, because the CPU is waiting, like, and this is the speed usually, let's say, if this is 1, this is 10, and this is 100. It's even worse than this. Let's to give you the relative speeds. You don't want to keep the CPU waiting. So all this processing, when something is not there and move it to the cache, we don't want to be taking much longer than 100. We don't want to take 200 to put in the cache every time you don't find something. That's called, by the way, a cache miss. So it reads a whole line, and based on the address of this line, let's say it was address 001101000, and it will pick the last chunk, and from this and I'm simplifying a bit, but apologies to computer architecture. But the point is that the cache line can find its place in the cache with just the value of the address and just taking a few bits of it. So this cache line can go in very particular places. Like if it were only like straight, let's say you have a cache of the size power of 2 and just take some bits from here and just put it in one position, it wouldn't be very useful because maybe your caches are in. You might have the cache with a lot of holes in there that are not used for because your data how use is kind of random. So the way it does a calculation from this, and it can define not just one single position it can go, but in multiple positions. And usually it's like 4-way associated cache or 8-way associated cache are the most common nowadays. For smaller things like what the processor might have in your phone, it might even be 2-way, but it usually should probably be 4-way. So with the problem we have here is that this calculation of where can things go is a power of 2 base because we're taking bits from here. And when we are navigating, let's say, let's make another. If we go back to the original, this is the original sorted with the numbers, 4, 15. If we do the plain binary search, we go from here to a half, let's say here, and the range was raised to this. And let's say then it wasn't here, so the range was raised to this, and then the next one is raised to this. You go like this. The thing is that the addresses, these are the addresses, the half of n address. This will be a quarter of n. These are inverse power of 2 relative positions that were working, especially at the beginning of the search. And given the associative n-way property of the cache to store data, it's very likely that these ones are going to fall in there. So what happens here is that this, and the equivalent like will be 3/4 here, and the very first few will fall all in saying this. Well, maybe a bit smaller. Let's say it's 4 positions, and there might be the first, I don't know, 32 or 64. We'll have to fit in this, so you will have a lot of cache misses, and each one of those is going to cost you a penalty of going to the RAM of 100 instead of having a penalty of 10 of going to the cache only. This is again, this is the problem is rooted in being accessing by address that you're looking for being proportional to the 2 to the minus something. So going back to this other one, this is the heap style order that we said the 2n plus 1. Let me adjust a bit. 2n plus 1 and 2n plus 2. Another excellent property of this, even though these are relative to 2x and 2n here, these are not powers of 2. So that problem of what is called aliasing, of kicking out of things that you want to use frequently happen to be in the same place, and so they are sort of kicking each other out all the time that you use them. That doesn't happen with this, because the order of the positions here, if you see, the first 3 are like 0, 1, 2, so are very different. If you take the last 2 numbers, the root will be, is it there? No, it's a bit too high. Let's move it here. Say root has address ending in 0, 0, 0. A has address 0, 0, 1. So you see right away it's like different, 0, 1, 0. If we're picking the last 3 bits, they're different. While in the other case, it was likely that the calculation you do to find the slot would be exactly the same. So this is a really good property of this. And this is kind of old stuff. It wasn't used for this, and it just happened to be good for caching.
Ale, sorry to interrupt.
Yeah.
Just to tell you, we have like five left, and then we should move on to a couple of questions. Sorry.
Oh, perfect. Yeah, thank you. Let me quickly go back to the Intel one, and I can close on that. So the way they do it to also have the property of what is called the fan out that you have in B+3. Remember, in B+3 you have the whole chunks of entries that you can, in each memory access, you can have many things that you can compare. They sort of combine it the same way. The way this is done by this Intel Oracle guys, this is called FAST. And it has a sort of repetitive name, like a recursive name of FAST architecture sensitive tree. So what they do is sort of the same as we had with B+3, but with applying this principle where the internal node, the nodes actually, yeah. The nodes are one after another. So it's one node. And the way, and the thing is now, instead of having two children that we had before in the binary search tree, you have many. So this goes to this goes to this, and you can have many. So the thing is, you can fetch one of these nodes and do a single memory operation. Also, there's the you probably heard of MMX and SSE and all those weird words that that you get with your CPU, and AVX is the last one. Where that also allows another interesting thing. They say you can compare several numbers at once. So what they do with this is, first, the memory access is the most important part. Like, you get a chunk of data in one go, as you could do with the B+3s. You don't, and in that chunk of memory is very compact. It only has the information that you need, the keys. There's no pointers, there's no position, nothing in all the internal nodes. And they do one comparison with this one. And in that comparison, instead of giving you, as we were before, with a binary search, this one can give you a position, like let's say position 7. You got, okay, with the key that you're looking, you compare, and it tells you and compares with all this stuff and say, okay, 7 of these are smaller than this one. So you can jump straight to the 7th and go straight to the 1. And so in each operation, you do more. You get more than 1 bit of information back. You get a lot, like a lot more, depending on the size of this, the amount of the comparisons. And another thing they did is to align those. This thing. I mean, also the way the memory is organized in modern operating system stuff is you have pages. You probably heard of. There's another problem there, that when data is very big, to find, it's kind of like you end up having like buildings, and you have to, like, and buildings of order, let's say. We were with the example before. So to find first which building a piece of thing is present into apartment that is doing that resolution is very expensive. So they also group, as we were grouping with B+3s, in chunks of memory that are all together. What they do is, in a whole page are the interesting things that you need, and in that order that we were checking before, the idea is that all the instead of putting in this layout, like one after another, you get all the top of the tree, because in that one you get the sort of the first one, second one. But then you end up having bigger and bigger holes in between, because the children of A and the children of B are in. Let's see, that's it. These are the children of A are in between children of B and B. You see, you have this. And at every step you're stepping, like if the distance from root to B would be A would be in the middle, and then for the next one, the children of B have all the children of A in the middle. So instead of doing it that way, the idea of this is you have in this would be R. Let's put it here: R, A, B, C, D. Let's say we can fit all this here. And we, instead of, because in this situation we have to walk, okay, A is right away, straight there. But if you have to walk the right side of the tree, this one will be a huge jump, and this will be also a bigger jump because all the E's are in between the E, the B, and the F. So they rearrange this in this way while keeping this navigational, and they can move it in these sub-chunks that are within a compact page. So yeah, and also they are very close together, so the CPU can say, oh, it is probably going to need something nearby. So it might even have, in one go, have most of it, or most of that it needs. The performance of doing things this way, if you combine the, well, first the size, like the size is like less than a quarter of the original size. Plus all this memory performance, it gives you like about 8 times to 20 times faster than the B+3s. But it's only for online analytics. You cannot use it for any other like things that need a lot of updates. Okay, sorry if I went a bit too fast. I was trying to
thank
do
you,
the
Ale.
topic in the talk. And thank you for.
Don't worry, super interesting.
Ale, instead of questions, we will do this. Just let the people know where they can reach you if they have something to talk to you, please.
Yes, I think, okay, I'll add my link to the event. So you can have the, where I have a page, and soon I'm planning to add a blog. The page is ologan.com, and it's going to be /blog. It's going to be the blog that I'm planning to start in the next few weeks, hopefully not months. And yeah, so any questions?
Everybody who wants to learn a little bit more about this can reach Alejo directly, and we will jump straight up to the last speaker in our list. Let me